As we move on to wave optics, one of the ways to figure out what's going to happen is to use something called Huygens principle. And to imagine this, we need the idea of a wave front. So let's say this blue dot is a point source of light, sends out waves in all directions. Now remember, the wavelengths for visible light are hundreds of nanometers, so this is very magnified. If we look at all these sine waves, if we look at the points, say, where they have their first maximum, that should be a circle. Then we say, okay, where's the first minimum? All these points, if we lined them all up, we'd have a series of circles going around this. Or in 3D, it would be spheres. Uh, this sphere is called the wave front. It's points where the wave is doing the same thing all along this. So they're all at a maximum, they're all at a minimum, whatever. If the waves are all going in one direction, like here, this next picture, they're all headed one way or the other, we can color code the maxima or minima, and like the red line, that's a wave front. The green line, that's a wave front. The blue line's a wave front. And it's just a wave front because all these waves have the same value of phase. They're at the same point in their cycle. So if we have parallel light rays, like from the sun, the wave fronts are also parallel. Now, Huygens' principle says we can figure out what's going to happen to light if we consider every point on the wave front to be a radiator of more waves. So in 2D, this would look like pebbles dropping in a pond. You drop a pebble everywhere along this wavefront. You get all these expanding circles. Then you connect all the a tangent line to all these circles. Well, you get the green line. That's the next wavefront. So we can find our next wavefront by looking at the previous one. Again, this should really be 3D, but we're fine working in 2D. If we look at how this explains refraction, we use the fact that the speed is different in the new medium, and that means circles that don't get as large in the same time. So they're smaller radius. We start off with this light ray, so that's like the laser pointer. The wave front is what we would imagine perpendicular to that ray. And if we imagine drawing these little circles everywhere and connecting them, we'll see these wave fronts move like just like the wheelchair axles that we drew. When we get down here into the new medium where the velocity is slower, these circles are smaller, and that bends the wave front. It'll be more useful to us when we look at diffraction, which is going to be something we'll do soon. If we discuss light as a wave, one of the most important properties it has is what's called linear superposition, which sounds intimidating, but it really just means we add two waves the simplest way possible. So if I want to know the x and time, the position and time coordinates of a wave, what I would do is add the position and time coordinates for each of the two waves that make it up. So for example, if we want to add the blue wave and the red wave, notice they're the same amplitude, same height, same frequency, the bumps line up. They're exactly out of phase. So this is a maximum where that's a minimum, vice versa. If I add those up, what I would get is the flat green line. I wouldn't get anything. They would completely cancel each other out. This is also known as completely destructive interference. If we're using light waves, what this would mean is this area is dark. If we were using sound waves, it would mean this area is silent. What if the waves are perfectly in phase instead of perfectly out of phase? Well, now when I add these two things, notice the change in scale here on this y-axis. I add them and the maxima happen at the same time, the minima happen at the same time. So here I've got 1 plus 1 gives me 2, minus 1 plus minus 1 gives me minus 2. It's exactly like the others, only it's twice the size. This is completely constructive interference. We could in general have any combination of these things. Like here, the waves are not exactly in phase and they're certainly not out of phase. So when I add the red and the blue, I get this green wave that is larger at the higher points than either of these, but it's not as large as two of them. So this would be partially constructive. The waves here are drawn about 1.1 radians out of phase. Remember, there are 2 pi radians in a complete cycle, so this is the same thing as being about 63 degrees out of phase. These guys were 180 out of phase, or pi radians out of phase. These are completely in phase, so 0 degrees, 0 radians, however you want to think of it. What we see here, this interference is constructive, is not completely constructive, because the amplitude of the green wave here is not twice the individuals, it's about 1.7. You could look at how waves with different amplitudes combine. We're not going to do it in this course, but the neat thing is, all you're doing is, again, adding. What's the red at a particular time? What's the red value? What's the blue value at that same time? Add them up and you get the green value at that time. So it's the simplest possible way we could combine these two things. We could even have different frequencies. So here the blue and the red obviously don't have the same frequency, same number of bumps per distance left to right. We don't have the same frequency, but we could still say, well, what happens when you add them up? You add the red value here at, say, 5 and the blue value, you get this green value. They almost cancel out. And we get this, if you notice, this very weird shape for this green line, and that's fine. It doesn't matter. It's not anything bad that we get these. And in fact, what you get when you do this in general is what are called beat frequencies. If you know anybody who plays an instrument and they want to tune that instrument to a particular reference frequency or match it with another instrument, they both try and play the same note. And when you listen, you'll hear a kind of a warbling back and forth that gets louder and softer over so many seconds. The closer they get to being in tune, the longer the period between those warbles. This is how piano tuners work. If you have a tuning fork, you tune the piano until the time between the beats is as long as possible.